Hello, everybody. Welcome to our class today. I wish that everybody did well in the quiz. I know some technical issue happened with OWL. We are figuring that out. That's why the marks delayed a bit. The mark you see in your grade book is just for multiple choice, not for the full quiz. So your mark will be updated, but we are figuring out with the OWL team how it's happened. And if there are two versions, we need from OWL team to send us the two versions. We have the latest version, but we need also the first version because some student, it's happened with them that they submitted twice. So we need to figure out these technical issues. However, in the next quiz, I'll make the essay question answer to be uploaded as attachment. So even the student has a copy of it to, make sure that these technical issues not coming out during the quiz. I wish everybody submitted their assignment 1 and 2. To be honest, I didn't check that in OWL. I did not check that in OWL. I did not check that in OWL. Just give me a sec, guys. Just give me a sec. Okay, guys. So I didn't look for assignment 1 and 2, but I will look for them tomorrow and we'll start marking them. You will receive your marking soon. I wish that I can release assignment 3 tomorrow, but we will see how our progress in the lectures. I believe that we can do that, but it depends. Other than that, we still have like 2-3 handout that they have some pumping lemma, some other calculation, but I believe they are easier than before. They are easier. We just finish the most difficult part in the course. The remaining part is easier. And I believe we will finish earlier than scheduled. So let's start. You receive the class note number 7. And the handouts also, I put handout, I believe 6, 7, and 8 today. So we are in a good standing. Let's see what's here. I had a question regarding the presentation. My group is presenting next Thursday, yet we have not received any information on what the presentation should include, what we expect the instruction to be released. Also, the instruction of writing the report. The report should have certain format. But no, it's not unfair. It's not unfair because as I told you, you will be marked on what you are presenting, and on the other hand, the report, it has the same deadline for all students, and the most weight is in the report. For a presentation, you have a topic. You have to talk about the parts of your topic. Each student should present. The presentation will be recorded. The presentations will be recorded. However, it will not be released because I need the camera to be open. But due to privacy, it will be kept for the course record only. So it will be confidential data. It will not be released to any other party, or it will not be posted in YouTube. I didn't say there is instructions for the presentation, guys. I clarified this since class 1. Each student should present. I don't want to like X to present half of the presentation and the remaining present like the other half. It should be equally. Like we have a 4 group member and we have 4 topics. Each one will talk about his topic with a limited time, with equal time, to be fair with each other. And the other instruction, also I mention it a lot, that each member of the group should be able to answer any question about what you are presenting. So I'm not expecting, for example, for the first group who is presenting, to present every single deep details about that topic. Whatever you read about the topic, whatever we reach to this point, and we need to present what we reach at. Yes, yes. And to make the thing easier for you guys, I chose topic from your curriculum. I didn't choose a very high advanced topic. I go to the course outline and pick the topic from your course outline. I didn't ask for anything you will not be taught during this course. For first group who will present next week, for first group, you will do whatever you reach at. Our topic is talking about this one. We plan to investigate, explore 1, 2, 3, 4. However, we reach at this point, X will present this, Y will present this, and I will ask you about the point you are reaching at. So don't tell me it's unfair. Is that clear, guys? I'm not asking you to fulfill all the topic. I need the whole topic to be covered in your report, not in the presentation. But those groups who's near the end of the term, you should be almost complete. I'm not saying fully completed because you have till the due date in April. In the report, I need you to do that. For the instruction of the report, it will be a format question, a format instructions. What is the font? How is the format? How to write your report? That's it. But for the topic, you have a topic from your curriculum. At least, you have to cover what we have in the class. At least you will have to cover the topics that we will have in our course outlines. If you wrote extra, that would be a bonus. So the minimum requirement is what we are taking in the course outlines. This is the minimum requirement. Let's say to get 80 to 90 mark, you will do whatever in our course outline. You do extra, you will move to the 90s, toward the 100. As simple as that, guys. Don't make things complex. And I don't use a sophisticated language. We are not in a, I have some students before, they try to make it like an English literature presentation. No, simple language, straightforward, so everybody can understand. And the main component, I need to know that the student in the group, they understand the topic and they can transfer their knowledge to their colleagues. So I'm looking for the benefit of the presentation, not the presentation content itself. Don't make it complicated. So I believe this is clear. Any other question about the presentations that will start next week? For the arranging, who start first, who second, I leave it for the group. I don't go to that deep details. I leave it to the group. You are a mature student and you know how to organize yourself. And it's a kind of an experience that if you have a group presentation at the work site later on after graduation, hopefully next year. Or the year after for those who will go for internship for 1 year. Clear, guys? Great. Sean, you send an email to the TA. I just explained that at the beginning of the class, Sean. I said the mark you are seeing is the multiple choice mark. For the second question, it's not marked yet. It will be a hand marking, and your mark will be updated. I just mentioned that at the beginning of the class. I just received your email. Okay, I understand. Also, I mentioned that in the quiz, during the quiz. Maybe you were busy or don't hear that. So the mark you see in your grade book, again, for all students, the mark you see in the grade book is the multiple choice mark, because I put the right answer in OWL. So I will mark your multiple choice. For the second question, it will be marked manually as of next week, because as I told, we have some technical issues. Some students, we have for them 2 answers. Some of the students make a couple of submissions. So this version, like for multiple choice, could be merged. And I need from our technical team to send me the both answers for those who answer twice, or for those who do a couple of submission and their long question answer, it's in their first submission. I don't have it, this version. So they promise to send it to me as soon as they can. Everything is recorded, don't worry. You will not miss any single letter you wrote. And if we found that technical problem, still some student, it was unfair for some student, I can make up longer question or do something to recover what they missed. So don't worry, guys. I'm not here to reduce your mark. I'm here to help you. Okay? So let's start. Okay. So let's open the handout number 5. Okay. Today we are talking about a larger class of computational models. We talk about the finite automata at the first part of this course, which include deterministic and non-deterministic finite automata, regular expression, and we prove that there are some expressions are not regular using the pumping lemma. And today we go wider to have another model, which we call it context-free grammars. Context-free grammars. At the beginning, we'll talk about context-free languages. Context-free languages. If you remember, or if you recap from previous classes, that we call our example 0 to the power n, 1 to the power n, where n greater or equal to 0 using the pumping lemma, and we prove that this language is not regular. That means there is no DFA or NFA or regular expression that can be describe it or be accept this language. So how we can describe this language? We know that the main objective of using computers or the computation system or computational model is to help humans to do sophisticated tasks as much as we can. So how we can expand the computational model to include these non-regular languages. How we can do that? We use what we call context-free language. We're ready to graduate to a broader class of languages, which we call it context-free languages, CFLs. The set of regular language is a subset of the context-free language. So regular language, REG, we used to call it before, is a subset or included in the context-free languages. That means L belong to regular language, then L belong to context-free languages. Though, as we will see, there is exist language M belong to CFL, for which M is not belong to regular language. And we call these languages non-regular languages. And we used to prove that these languages are not regular using the pumping lemma in the previous classes. So here, a small diagram and a simple diagram that show how we are limited and how we can expand the computational models to contain more sophisticated classes. So with regular language, we study the DFAs, NFAs, and regular expressions. With context-free grammars, we will study context-free grammars and push-down automatas, which is the broader class. Then we have what we call it context-sensitive model, but this is beyond our course scope. Then we will study one model of the recursively enumerable model, computational model. We will study one model, which is the Turing machine, Then we'll be done, and we'll move to the complexity part and decidability of the languages. So once we finish this one, we still have one more model, which is the Turing machine, which we will be study. Today we'll talk about part of it, and tomorrow we'll try to continue this model. Representing languages. So the language, it's automaton-based or expression-based. If the language is automaton-based, it's either could be automaton-based or expression-based. If the language is, so we'll talk about the language. Is it automaton-based or expression-based? Is it regular or context-free or context-sensitive or recursively enumerable? These are the model that we have here. Regular, context-free, context-sensitive, and recursively enumerable. So if the language is regular, as automaton-based, we have the DFA and NFA. Expression level, we have regular expression. If we talk about context-free grammar, we'll talk about push-down automaton, and we go to context-free grammar, which is the depend on the expression. Context-sensitive, we have linear bounded, not studied, and context-sensitive grammar, which is not studied and beyond. This one, if you study a master in programming languages, you have to take the advanced computational theory, and this topic will be covered there. Recursively enumerable, we will have the Turing machine and unrestricted grammar, which is also beyond, it's a complicated and sophisticated topic, which is beyond our discourse scope. So in the previous lectures, we studied DFAs, NFAs, and regular expression. This lecture and part of today's lecture also, that's why we extended. And tomorrow's lecture, we will study the push-down automaton and the Turing machine. And at that point, we are done with computational model. Then we'll talk about some complexity thing. Grammar. A grammar is a set of rules governing the structure of the string. In a natural language, it describes how sentences are constructed. If we have a sentence, noun, phrase, verb, phrase. If it's noun phrase, then we'll say either it's a complex noun or complex noun followed by prep phrase. If it's a verb phrase, it will be a complex verb alone or a complex verb followed by prep phrase. What is the prep phrase? It is the prep complex noun. Complex noun, it's article noun. Complex verb is a verb or a noun phrase. Article, a letter A or the. Noun is boy, girl, flower, etc. Verb, touches, likes, flower, whatever. Prep, with. So this is the kind of a grammar. If we are talking about natural language or the normal English, either the sentence could be consist of noun phrase or verb followed by verb phrase. The noun phrase could be 1, 2, 3, the verb phrase, etc. So this is the way that we put the rules of the grammar. So we'll follow the same model to talk about context-free languages. Let's build a sentence with this grammar. Noun, phrase, verb, phrase, complex noun, verb, phrase, article, noun, verb, phrase, a noun, verb, phrase. So we replace the article with a. Then a boy, which is the noun, verb, phrase. A boy, complex verb. A boy, verb, a boy sees. So this is how we follow. As you know, from the first class, we said that the computer is a machine. So we have to give it each simple step that we may do as human in order to do the computational model correctly. And we have the correct output. So notice how we start out with a set of variables. We call these variables. And then we replace those variables with the words or other variables. We keep going until that's left is words. We have used the grammar to produce a valid sentence. These are the steps, guys. We will see now how. I'll give you a lot of examples to let you understand. When we say about context-free grammar in programming languages, what does that mean? A context-free grammar, CFG, is a formal grammar that describes the set of context-free languages. A context-free grammar is a for tuple, which is V, sigma, R, and S. V, which is the variable, a finite set of variables. If you wanna say it is something similar to the alphabet with regular expression. Sigma, a finite set of terminals. A finite set of rules R, or what we call it production rule, which a variable may be replaced with some concatenation of variables and terminals. The terminals, which is, if you remember when we said let's L has a string S, S belongs to 0, 1. So the terminal are 0, 1. The terminal are 0, 1. S, which is the string, it's the variable. And we have some production rule how to change S to a string. And S should belong to the variable. And we said V is a start variable. We will see now how. A language is context-free if and only if there exists some context-free grammar that describe it. So we have a context-free grammar and we have non-context-free grammar. And we will use the pumping lemma again to prove that this language is not context-free grammar. Context-free grammar, the idea. A context-free grammar is similar to a regular expression. It's like recipe for producing strings, which is some 4 steps that we have to follow or some steps that we have to follow to change that grammar. Either I give you the language and ask you to produce a grammar that describe it as a context-free, or I give you, this is a context-free grammar, identify the language belong to that grammar. The set of all strings that can be produced or derived by this recipe constitute the language described by that grammar. The idea is you start the first variable, from there you can substitute variables for variable terminal as per production rules. When there is no more variables, you stop. You remember for a friend example, first example that we use with pumping lemma, that we prove that 0 to the power n and 1 to the power n, where n is greater or equal to 0, it is not regular expression, right? But watch how easy it is to describe with a context-free grammar. We have a variable A could be replaced with 0, 1A or epsilon. The interpretation of this production rule is start with A, then any instance of A can be replaced either by 0, 1A or an epsilon. Let's see. Suppose we use this grammar to derive the string. If we wanted to arrive to 0, 0, 1, 0, 0, 0, 1, 1, 1. We'll start with A. And we replace A with the first rule. We choose the first rule, 0, 1A. It will be replaced with 0, 1A. Then we again choose to replace A with 0, 1A, which is the first production rule. It will be 0, 0A, 1, 1. Then we decide again to replace it with a 0, A1. And from before we have 0, 0, 1, 1. Then we decide to replace A with an epsilon. So we'll have 0, 0, 0, 1, 1, 1. And there is no more variable to be replaced. We stop at this point. Clear till here? Questions? Ask by voice. Don't send chat messages.
Sorry, sir. I just have a bit of an unrelated question. I got my final exam schedule, and I noticed that there's an exam for this course on that exam schedule. So I just wanted to confirm with you that we don't have a final.
We don't have a final. I will email the secretary. I think it's a mistake by the undergraduate secretary or coordinator. I'll send her email telling her there is no final exam for this course. So they will remove it. No worries.
Perfect. Thank you so much, sir.
You are welcome. Guys.
So for context free, like the whole point of the variable is to like maintain like that memory, I guess, portion of the language.
Don't jump to handout 6 or 7.
Okay. Okay.
Yeah, guys, you will see all these computational model. We don't use memory yet, right? With Turing machine, we'll start to use the memory. Here we have a grammar. We just do a parse it, and either with each variable we replace it with one of the production rule. Here, for example, for this example, we have 2 production rules. Either I replace the variable A, this is the starting variable. Either I replace it with 0, A1 or with epsilon. Okay?
But
now,
I'll
ask a question. I will ask a question.
Okay.
Who can tell me if I give you this example and ask you, give me the language that is accepted by this grammar, you will write L equals 0 to the power n, 1 to the power n, where n greater or equal to 0. Or if I give you this language and ask you to build or construct a context-free grammar, you will have to think, okay, I should have the equal number of zeros and equal number of ones. So I have at that time 0, A1, which means at each 0, I have a 1 to match it. Then I can replace it with another 0, A1 or an epsilon. So I'm giving you different scenario that you can see the question. We'll see now in the examples. Okay, let's take example number 2. Context-free grammar, example 2. One important application of CFGs is to compiler theory in application of a well-formed parenthesis. So we should have a balanced parenthesis. With each left parenthesis, we have the matched right parenthesis. So we don't have the left has more, we have, or assume that we have a more parenthesis from the left side more than the right parenthesis. No, it's not accepted. Or I have more right parentheses than the left parenthesis. Also, this is case as not accepted. It should be balanced case. So it's either I should think about the scenarios. I ask you to put the context-free grammar that describe this language, which consists of balanced parentheses. How we can do that? We have one of 2 cases. Either I have parentheses inside each other, or I can have left, right, left, followed by left, right. How can I produce these kind of context-free grammar? The first one, if I have parentheses inside each other, I write parentheses as parentheses. But if I'll have left, right, then I can put it as SS beside each other to have it, so to simulate all scenarios of the parentheses or epsilon. Again, the interpretation of the production rule is start with S, then replace any instance of S with left S right parenthesis in a balanced pair of brackets or in a split into two components, and epsilon, which is the empty string. So assume that we ask you to derive this. In the class note, it's more generic example. So assume that we'll have this scenario that we need to do it. Then we have to start with S. Then we'll make S left S right. Then left S right. We replace S here with the second production rule, which is SS. Then we change those one with first, each of them with first production rule. Then we replace them with epsilon, and we have the scenario that we ask to derive. So no more that variable, no more variables, so we stop. Just wait, just give me a sec, guys. And working from home. Okay. Now, let's have another example. Let L equal W. W contains more zeros than ones. How we can simulate this one? No, spider are not scary, Trevor. Okay, let's continue. She thinks that she saw a spider. There is no spider, but she thinks that. Okay, so that our string W, that it has to contains more ones than zeros. Let's begin considering the string that contain no zeros. We'll still need at least one, so it contain more ones than zeros. So let's start off that rule. So this is the first rule. I have to think about it. So I'll make S equal T1T. You can use V equal S1S. But note that I would not accept any variable in a small letter or lowercase. All variable, it's a rule. All variables should be written in an uppercase. I put it in the class note for you. I wrote that in the class note for you. Now, what should T be? We'll let T to be replaced by epsilon, then we can terminate any T at any time, which is seem useful. It is useful, but it's not cover all scenarios. What about zeros? So next, we need a rule that guarantees that at any time we add a zero, we also add at least one. So T, it could be either 0T1 or 1T0. So when we add any zero, there is a 1. And at the beginning, we have a 1 added. Also, what about only ones? To add more ones than zeros. So we should consider another production rule that contains one only. So we'll say T will produce 1T. Finally, we need the ability to spawn more variables in order to make arbitrary combination of these above rules. Then we can say T can produce TT, which could be either this one or the first rule. So S will give T and T1T, and T could be either TT or 1T or 0T1 or 1T0 or epsilon. So here we take all scenarios that will give me that the number of zeros is less than the number of ones. Try a few different derivations to convince yourself. There is no way for this grammar to produce a string with equal or more zeros than ones. Here, we make sure that the number of ones at least more than the zeros, even with one instance. It can produce any other string. Regular languages are context-free languages. So you'll ask me, we talked from the beginning of the class about non-regular languages. What about regular languages? It is a part or a subset of context-free languages. So there is a sorry. There is a theorem that every regular language is a context-free language. Recall a language is a regular if there exists some DFA that recognizes it, and the language is a context-free if and only if there exists some context-free grammar that generates it. Therefore, to show every regular language is a context-free, it is sufficient to show every DFA has an equivalent CFG. So I'll give you some example about the DFA has equivalent CFG. To convert a DFA, a deterministic finite automata, to CFG, we said all static QI belong to Q become variables, we call it QI. All symbols S in the strings before belong to sigma, which is the alphabet, become terminals. All transition row or delta, small delta, QI times S will give me a QJ, new state, becomes rules, QI to SQJ. Start state Q naught will become to Q. First rule is a Q naught. All transition into an accept state QF belong to F become rules. And then one of the QF will take us to the epsilon to stop that conversion. For example, if you receive a question, convert the following DFA to a CFG. The DFA that we have, Q naught, if we receive 1, we'll stay at Q naught. If we receive 0, we'll go to Q1. Then if we receive a 1, we'll stay at Q1. If we receive a 0, we'll go to Q2, which is an accepted state. Then if we receive a 1, it will be an accepted state at the end. So following our conversion rules, this yields to Q naught will give me 1 Q naught or 0 Q1, right? And the Q1 will give me 1 Q1 or 0 Q2. Q2 will give me 1 Q2, and if I receive a 0 or whatever, it will take me to epsilon. These are the conversion rules. Great, guys. So now we will move to our class notes for this class. Can you see it? Can you see the class notes?
Yes, sir.
Okay. So again, we will repeat the handout in a simpler way and assume that I'm writing this in the board. So we are recognizing a larger class of languages than regular languages. We go wider, as I said in the beginning. Application in programming languages and compiler design. We use these things in building the compilers and in programming languages. Informal description, we have the formal description taken in the handout. So here, how we will solve the questions. This is the most important thing for you guys to get marks. So we have a terminal symbol, which is similar to the alphabet symbol, 0 or 1, A, B, C, or whatever we have in that language. Variable symbol can be replaced with a string of variables and terminals, both. Production rules dictate how variables get replaced. We'll give a rule how we can replace the variable. Then the start variable, which is the starting point of the computation. How computation happens? We have 3 steps. Write down the start variable as the current string. Pick a variable in the current string and replace it with one of its production rules. Continue step 2 until no more variables are left. These are the 3 steps that you need to solve any question. Here I put for you note, variables are denoted with capital letters only. Don't put it in the exam in small letters. Okay, terminals. This is an example we have, which is the first example that we have. But here I make it vice versa. If you receive it, if we have the following CFG, what is the language that it describes it? Okay, or accepted. So we have this production rule. The variables are S. S could be 0, S1, or could be an epsilon. Start variable is S. So, okay, I'll start with S. I replace it with first production rule. I'll not go to epsilon from the beginning. So it will be 0, S1. Then I replace this S with 0, S1 again. So we'll have 0, 0, S1, 1. Then we'll go to 0, 0. Again, we replace it with 0, S1. So we'll have 3 zeros, S3 ones. Then we change it with epsilon. So we'll have 0, 0, 0, 1, 1, 1. Assume that I give you W 0, 5, 0 to the power 5, 1 to the power 5. Okay. So I'll ask you, is this string accepted by this CFG? You will check S equals 0, S1, then 0, 0, S1, 1, then 3 zeros, 3 ones, then 4 zeros, S4 ones, then 5 zeros, S5 ones. Then we'll change this one with epsilon. So we have 0 to the power 5, 1 to the power 5. Hence, W is accepted by this grammar. Every string of the form 0 to the power n, 1 to the power n, where n is greater than 0, is accepted by this grammar. Does the grammar accept any other language? The answer is no. So this grammar will accept the language 0 to the power n, 1 to the power n is greater or equal 0. So here's the first example that we took in the handout, but I do it in the other way. If we have this context-free grammar, what is the language that is accepted by this grammar? So the question can come in 2 ways. What is the language accepted by this context-free grammar? If we have terminals are zeros and ones, the variable S, A, and B, production rules as S, which is, will send any A as B, or S to epsilon. How we denote this? We write it and we put the column to replace or the comma. So this is the formal way that we describe the grammar. A will take me to a 0, then B will take me to a 1, 1. Start variable is S. Now here's your choices to find the language. So as here, I put in the top what we replace it with to understand what we are talking about. As we replace it with A as B, then we replace A with 0, it becomes 0 as B. Then we replace it again with first production rule, which is A as B. So it's become 0 A S B B. Then we replace S with epsilon. So it's become 0 A epsilon B B. Then it's become 0 A B B. We replace the first B with 1 1. Then we replace the second B with another 1 1. Then we replace the A with 0. So we have 0 0 1 1 1 1. So I think it's clear that the number of zeros is half number of 1. So how we describe this language? The language accepted by this language is 0 to the power n, 1 to the power 2n, where n is greater or equal to 0. Clear? Questions? Okay. Let's take another example. If I give you the language L1 equal A to the power n, B to the power m, where n is greater or equal to 0, and n is less or equal to m, and where m is less than 2n, which means that the number of zeros is less than the number of a's is less than the number of b's. As maximum, the number of b's should be double number of a's, but it could be less. How we can do this one? So we'll make it a as b and epsilon. A could be a, and b, if it is equal to the same number as minimum, so it will be b, or if it will be as maximum bb, then we'll change it to bb. So we'll take all scenarios. Now, if I ask you to do the second example, if we have L2 that consists of a string w, w belong to 0, 1 star, number of zeros in w equal to number of ones in w. So here is the same example of 0 to the 1, 0 to the power n, and 1 to the power n. So equal number of zeros. So S could be, here what we see, with each zero, we should have matched number of 1, equal number of zeros and 1. If we start with a 0, then there should be 1 somewhere to match this 0, like the same example of parentheses. So we put the production rule as 0 as 1 as 1 as 0 as. If we start with 0 or we start the string with 1, then epsilon, then we can change any one of them. Okay, the language of balanced parentheses, the same one, we take it, a string over left and right parentheses such there are balanced and well matched. So this one is accepted, this case is accepted with a separate one or a split one, this one is not accepted, and this one is not accepted. So here how we will write it, L3W equal left and right parentheses star, W is balanced. S equal or SS or epsilon, we took the same example, and here how we move in between them, and we have this example. So regular languages are context-free grammar. So let L be a regular language, then there is a DFAD with these tuples such that L equal L of that DFA. Construct a CFG, then we write variable or V, which equal Ri, where Qi belongs to Q. If delta Qi send me to A, then it will go, and I receive an A, then it will go to Qj, then add the rule Rj to Arj. If Qi belongs to F, accept the state, this mean, then add the rule where Qi belongs to sigma, start variable is R0. So here we are done with the handout 5, and we talk about context-free grammar and how we can convert a DFA to context-free grammar, and these are the rules that I need based on this diagram, and how those could be changed. And any regular language is a context-free language, and non-regular language also a context-free language. Some. Okay, clear, guys? Do you want a break? Yes or no?
Yes, please.
10 minutes or 5?
10 minutes.
Okay, Rochelle, go ahead. So you have a 10-minute break, guys. See you after 10 minutes. We will start with handout 6. Zoom recording, okay. Okay, we'll start with handout 6. We'll not have the class notes for this handout. We'll have it tomorrow in our class tomorrow. So the pushdown automata and pumping lemma for context-free languages. Recall our standard example. The language that consists of zeros and ones, and they have the same number of zeros and ones where n equal greater or equal to 0. We use the pumping lemma to prove L is not regular. Then we gave the context-free grammar that generate this language, which is 0s1 epsilon or epsilon. Recall grammar are like a recipe of generating a language. On the other hand, automata are devices for recognizing a language. In this lecture, we're going to look at the class of automata for recognizing the context-free languages, push-down automata. And if you remember, in the figure that, in the table that we have in the previous handout, we said that the context-free grammar, if we talk about automata or automaton, we will talk about push-down automata, which is connected topic to what we talking about in the previous handout. What is the push-down automata? Consider an NFA, non-deterministic finite automata, reading input A, B, B. In this example, it starts at the left at the A and moves to the right one symbol at a time. Assume that we have, guys, I don't know if you remember the normal tape, recording tape. Do you remember that? Assume that we have a recorder using the normal tape that's 2 circles, and it has just only forward. We don't have backward. If we have the backward, we'll talk about Turing machine, which is the next topic that we will cover. So here we'll push A, then we'll push another A, then B, then another B, etc. Okay, a push-down automata is essentially a non-deterministic finite automata with added ability to read and write from a stack. You know the principle of the stack? We will add symbols, and once we pop a symbol, which will be the last symbol in the stack. Each time it reads input symbol, it also reads the top of the stack and do stack operation. What do you mean by stack operation? We'll see now. Push-down automaton definition. It is a 6-tuple, which consists of a Q, sigma, rho, or tau, some of them call it, which is delta, Q naught, and F. Q is a finite set of state. Alpha is input alphabet. Then tau is a stack alphabet. Delta is a Q by sigma epsilon or tau epsilon will give me a new transition function P, which will be the Q times the rho epsilon. Q naught is a start state and F is the accept state. Next class, with explanation and example, you will understand everything. From the definition, we see that transition involves the current state, the current input symbol, and the current stack symbol in the top of the stack, and yields a next state and next stack symbol. A, B will have the C, which can be read as reading A on input and B on top of the stack, then will be replaced B with C. Again, guys, what do we mean by this? If I read A and B at the top symbol of the stack, we'll replace B with C, because we are stacking symbols. A equal epsilon, we make a transition without reading an input symbol like an FA. B equal epsilon, we make the transition without reading or popping from the stack, because the stack has 2 main operations, pop or push. C equal epsilon, we make the transition without pushing anything to the stack. So these are the rules. If A is epsilon, we'll do the transition without input symbol. If B equal epsilon, we'll do the transition without popping any symbol from the stack. If C itself is the epsilon, we'll do the transition and will not push any new symbol to the stack, to the top of the stack. Using this notation, we can define a set of stack operation, push X, epsilon Y. If you read X on input, push Y immediately. This is the translation of what we said before. If we pop X and Y, epsilon, if you read X on input and Y on the stack, push epsilon, which is literally push nothing, replace X, Y, Z. If you read X on input and Y on the stack, push Z, replace Y with Z. Do nothing. If X epsilon, then epsilon. If you read X on input, do nothing to the stack. Bottom of the stack, technically the stack is a string, is initialized as epsilon. So the first symbol we push to the stack is epsilon. Depending on application, you may wish to push an explicit bottom of the stack when automaton style. Push down automata example 1. Recall our language 0 to the power n, 1 to the power n, where n is greater or equal to 0. Let's draw a PDA that recognize this language. Here, what we will need to do, mark the bottom of the stack so we will know if when we encounter it later. Start pushing all the zeros onto the stack. As soon you see a 1, start popping items of the stack. Pop 1 at the time for each one. You see if the stack become empty upon seeing last one, then you saw equal number of zeros and number of 1, then accept. What do we mean by this? In this example, we'll push the zeros. Once we see, now with each time, because the language consists of zeros first, then ones. We don't say 0, 1 star. It's different. Example. Here, our string or the language consists of zeros at the beginning, then ones. Equal number. How I can accept this state? We will use the stack. At each time, the push down automata will push zeros. Once we see the first one, we'll pop first 0. Then second one will pop another 0. If we end at empty string, then we will accept, which means that the number of zeros equal to the number of ones. If we still have remaining ones or we still have remaining zeros in the stack, that means the number of zeros is not equal to the number of ones, then we will reject that language. Putting this together, we have start Q1, mark bottom of the stack with epsilon, that this is the bottom of the stack. Q2, read through zeros. If zeros on input, push zeros to the stack. Start reading ones. If 1 on input, pop 0 from the stack. Read through ones. If 1 on input, pop 0 from the stack. Is it the bottom of the stack? Yes, accept. No, reject. Clear, guys? Clear? Okay. Or rewritten in our transition notation, epsilon, epsilon. This is the first thing. We push epsilon to the stack, or this sign, which show me that this is the bottom of the stack. You said, I don't want to put epsilon at the bottom of the stack. You put any other symbol to let the language know that this is the bottom of the stack. Then if we receive a 0, push 0. Once we read 1, pop 0 and replace it with epsilon, which means make the cell empty. Then we read 1, also pop another 0. Is here we reach to the state epsilon with this symbol and we replace it with epsilon? If yes, accept. Okay, more zeros. If we have more zeros than 1, then there will still be zeros on the stack. This is what I said before. When the computation stops, and thus we won't be able to transition to the accept state Q4. More ones, if we have more ones than zeros, then as soon as we run out of zeros, we'll see that as symbol and the transition to Q4. However, since ones are remaining in the input and no defined transition of Q4, the computation proof dies. Out of order zeros and 1, same as before, as per the transition, there is nowhere else for the computation to go. So it also proves dies or proofs. Sorry. Now, equivalence of push-down automatas and context-free grammar. A language is a context-free grammar if there exists some push-down automata that recognize it. To prove this, we will follow the same strategy when we prove that the equivalence of DFA and NFA. Prove that every CFG generating the language L, there exists some PDA recognize L. See lemma 2.2 in our textbook Spicer. A proof for every PDF recognizing L, there exists some CFG generating L. See lemma 2.27 in Spicer or Sipser. Pumping lemma for context-free grammar. You love pumping lemma, right? Non-context free language. Consider the language A to the power n, B to the power n, where n is greater than 0. We prove in this language is non-regular using the pumping lemma for regular language. And the result of our study thus far, as shown as CFG and PDF, are capable of some form of counting. But just how many things can CFG or push down keep track of? Can we consider all situations? Of course not. Now consider another language. L prime A to the power n, B to the power n, C to the power n, n greater or equal to 0. Now we need to keep track of three things. Is there a CFG or a PDF that can generate or recognize L prime? It seems like no. Recall our solution to L was to push all the A's onto the stack and pop them off to match each of the B's. But if we try to do this for L prime, we were done comparing A's to B's, we're left with an empty stack. So how can you compare C's if there is nothing left in memory to compare to? So if we compare two things, I can't do it in a stack. But if I compare three things, first I will compare A's and B's, then how I can compare them with C's. Parse tree. Here we'll have what we call parse tree. Let L be language and let S belong to that string. If L is a context free, there exists some context free grammar to generate S. We can derive S beginning with a start variable S and substituting variables or terminals according to the grammar until only terminals remain. Recall in the pumping lemma for regular language. If a string was long enough, then by the pigeonhole principle, it must revisit a state within the automaton forming a loop. Let's extend this idea to the context-free grammar setting. If a string is long enough, then by the pigeonhole principle, it must revisit a variable somewhere during the derivation. Same principle. Consider the following grammar. If we have S, A, T, B, T, either could be A, T, and then B, or epsilon. Suppose we want to generate the string AABB under the following derivation. S will give me ATB, then AATBB, then we replace the T with epsilon, then it will be AABB. The variable T was repeated, that is T is substituted for something that led to another T. And like in the pumping lemma for regular language, we can pump this loop and the result should still be in our language. But with regular language, we use with pumping lemma XYZ. Here we'll use 5 symbols. We'll see. The diagram depicts a loop, a variable T that follows a derivation leading back to a T. The resulting string S can be segmented into 5 parts, U, V, X, Y, and Z. U, V, X, Y, and Z. This is what we know before. Here we add a U, V. another 2 parts. Notice that outcome of T to T loop is strictly contained in substring V and U. So here we have S, T, T. Here we can call it U, V, X, Y, and Z in the parse tree. Pumping derivation. Okay, so what happens if we substitute one of the T's with another T to T derivation? We pump it 1. If S equal U, V, X, Y, and Z, and V and Y are the result of T to T derivation, then if we repeat pump the TT segment to something of the form of TTT, then VY section will be repeated. And we'll have here UV, V, X, Y, Y, Z. If L is a context free, then S prime must be a member of L. So to most that S double prime UV to VXY, then YZ. Similarly, we should be able to remove T to T segment and hence V and Y substring and still have the result be a part of the language. So if S, U, V, X, Y, Z belongs to L and L is a context free, then it must be also a case S prime that U, V to the power I, X, Y to the power I, Z. If you remember, before we use these 3, here we add U, V, I. Belongs to L for all I greater or equal to 0. We will solve a lot of questions, don't worry. So what is the rule of pumping lemma? If L is a context-free language, then for all strings L, S belongs to L where the length of S greater than the pumping length P, then S can be divided into 5 parts, S, U, V, X, Y, and Z, where U, V, I, X, Y to the power belong to L for all I belong greater or equal 0. The length of VY greater or equal to 0 must, so it's not empty. It's not empty, not only greater than 0. It couldn't be a 0. And VXY less or equal the length of it, the P, which is the pumping length, so is no greater than pumping length. So this is our example that we talk about. A to the power n, B to the power n, and C to the power n is greater or equal to 0. Example 2. We will have next class, use the pumping lemma for context-free language to prove that the following language is not context-free. WW where W belong to 0, 1 star. So we will prove this also is not context-free language. Now, languages and classes. We have looked at both continuing counting and string copy languages. Here is table showing the capabilities and limitation of each language class. If we have a regular, cannot count or unbounded, we cannot do counting with DFA and NFA and regular expression. Also with string copy languages, we cannot. Context-free, 2 things, we can do it, but we cannot copy forward like WW to the power R. Context sensitive, up to 4 things, A to the power n, B to the power n, C to the power n, D to the power n, single copy WW, and we said this is out of our course scope. Recursively enumerated, which is the Turing machine, unrestricted A, n to the power n, etc. So also unrestricted WWW, it will be solved also with the recursively enumerable, but also this other part with the string copy languages is outside of our course scope. So those 2 things, this one and this one, is not part of our course. So tomorrow we'll have those and we'll talk about Turing machines. Okay, I'll stop here and I'll not, because we still have only 15 minutes of the class, or literally 8 minutes, because each hour equal to 15 minutes and 10 minutes break. So I don't have enough time to start with class note 7 that will solve all these things with example for Pushdown Automata. Then we'll have a couple of example about pumping lemma. Then we'll move to handout 7 tomorrow. which is the Turing machines. In Turing machine, we have some memory places and we can move left and right, which will solve something different. And we'll have here some examples, and with the state transition with all these things, and we will see example of a to the power I, b to the power j, c to the power k. This example with multiplication, how these things could be happen using Turing machine. And by end of tomorrow or Saturday, we will release assignment 3, and will be on the cube. And we'll still have like 8, 9, 10, and 11, and 12, but they are short handout and simple handouts. See you tomorrow, guys. Have a great night. If there is any question, you can stay. If you don't have a question, you can leave.
Hi, I have a question.
Yep.
It was related to one of the slides you had up not that long ago, where you're saying, how can we make the state model for a language, like if it was A to the N, B to the N, C to the N? And
Which one
I
here?
was wondering.
Just
Sorry?
a second. Just
if
a
you could pull
second.
that up.
Can you see
Yeah.
here?
Yeah, next one, it was, yeah, so this one, oh yeah, could you go back there? So for this one, we had, it was basically just A and B and making sure that the two were the same size.
Mhm.
But in the transition between Q2 and Q3, you put the empty string onto the stack, and that kind of, well, that empties the stack. But so what if instead of that empty string, you put in the input into the stack? So then you could kind of keep count of that one. So if it was A to the N, B to the N, C to the N, then you put A onto the stack and then make sure that A and B are the same number. And then while you're doing that, you push B onto the stack.
How you can do that? Can you tell me? How you can compare 3 numbers or 3 components, they are equal in a stack?
So I was thinking, okay, well, could you
With
tell
the
me then
Turing
why
machine, you can.
Yeah. Okay.
Because
I
you
think
can go left and right.
Mm-hmm.
But if you cannot go left and right, because you know the stack, first in, last serve.
Mm-hmm.
So how I can put A, B, or C, and I count, and I can, how I can do 2 pops, like if you can do 2 pops in the stack with one transition, but how you make sure that they are after each another? You cannot. So that's why I told you in handout 6 that with this model, I can compare, because I'm using a stack, I can compare 2 components.
So
but
I think
if I go to context sensitive, I have a memory, I have a counter. Here I just have a counter, 2 counters.
Okay. So
Yeah,
so
here
the counter,
I have multiple counters, so I can solve it. It's solved computationally, it's solved. And what you're saying is correct, but not with a stack structure.
Okay,
You have with random memory structure, yes.
Yeah.
That with
What
each
about
symbol, I save the address of it, and I check with the list of addresses I have. With the list of memory addresses I have in hexadecimals, that I have this symbol, then I can make, like, you know, in C++, if you said, let's C equals 0, A equals 0, and B equals 0. And every time you read an A and B, you add your counter, and each time you pop A or B, or you at the end, you can check, is the number of A equal the number of B or equal the number of C, yes or no?
Okay.
Yeah.
I think, yeah, that makes sense. And so,
So with random memory access, I can do it, but with stack structure, I cannot.
okay. And so then what about in the recursively enumerable? Could you do the same thing if you had A to the N and then B to the M, for example?
We will see tomorrow.
Okay, okay. Thanks.
Okay.
Have a good day.
Okay. Okay, Danielle, go ahead.
Hi, I submitted an SRA for the quiz 1. Is there a makeup for that, or would there just be a shift in the percentage?
What do you mean?
The self-reported absence, I submitted one for
Yeah,
quiz.
for those self-reported absence, there is no shift for the marks. I will assign time slot, but I was waiting the students because they give them like 48 hours to report their absent, and they have 48 hours to contact the instructors. You know, and
Yeah,
if we
I emailed-
consider the weekend, I don't want it to be, you know, very strict with my students. So I consider Saturday and Sunday are not part of those. So today is the end of the second 48 hours. I like if they like it was on a Friday, so if they did report the absence on a Tuesday, because the first 48 hours end in a Tuesday, then they have the 48 hours to contact me, so they have till end of today. So by
Okay.
tomorrow, I will make the full thing. Then I will send an email for those who has the self-reported absence, or for those who has certain situation or medical leave, and they use this leave instead of self-reported absence. Because you know you have two chances of self-reported absence. Some student will make it for something, not a quiz, maybe something better for
Yeah,
them.
okay.
So they submitted to the department, to the secretary. So she said to me that tomorrow she will send them these leaves to approve them and the counselors. So I'm
Okay.
waiting till tomorrow. By next Monday, you will be notified.
Okay, all right. Thank you so much.
Don't worry, don't worry. I'll do a quiz. I know that, you know, we have 150 students. If like we are, I think 11 student or 12 student, they have certain similar circumstances, which is very normal percentage. So I'll not take anything against the student. I will do a similar quiz for you guys. We will assign a certain hour to do the quiz, and you will have the same time, an hour, same as them.
Okay. All right, Monday. Okay, thank you so much.
And Monday, I will let you know the time and when we will do the quiz.
Okay, thank you.
Good luck.
Yes,
Questions?
sir. I'm just waiting for everyone to leave so I can ask my question.
Okay, Vishal. Okay, Vishal, do you have a question? Sean? Sean? Sean, it seems he's not on his desk. Sean? Okay. Okay, I'll stop recording here. Wait, Miti. I'll stop recording here. Since you don't want your colleagues to hear your questions, so it's okay. I'll stop.